triangles, and it's going to end up giving you the same thing, right? Because this half triangle is going to come over here, and you could put it right there, and it would look like a rectangle, right? So you get the same area. So that's parallelograms. Now trapezoids are a little bit different, right? So a trapezoid has one set of parallel lines and one set of lines that are not parallel, okay? So it could look like that, or it could look like this, or there's any number of shapes that a trapezoid could have. And the way that you calculate the area of a trapezoid is it's fairly interesting. What you do is you take the average of the two sides that are parallel, right? So you pretend that you've got a rectangle that ends halfway in between the length of this and the length of that. And then you just multiply base times height. So it's actually going to be height times, well, and the way that you would get this, the way that you get the this average length is you say width 1 plus width 2 divided by 2, right? Okay, so that's going to be your area for a trapezoid, because your width 1 is, let's say it's this leg and it comes all the way out here. Width 2 is this leg. Well, if you add those and divide by 2, then what you get is you get the average length, right? All you're doing is taking the average length. So you take the average length, multiply it by the height, and boom, that's your area of your trapezoid. So there you go. And they show you some other methods of calculating, of arriving at this same formula. But that's the formula for the area of a trapezoid. Okay. Now then, let's move on to 117. Equations with x squared. Okay, so that's called a second order equation. An equation with x squared is called a second order because you've got so equations involving x squared, it's called the second order because of that exponent of 2. It's called a second order equation. Second order, okay? So we're talking about second order equations. So one of the things that they're going to point, and you can get, trust me, in algebra, they're going to get really complicated with their, with binomials and polynomials and all these second order equations and quadratics and so forth. But one of the points that they make is that to bear in mind that whenever you're taking the square root of a number in order to solve a problem, the root can be positive or negative. So if you're taking, for example, if you're taking the square root of the number 16, that can be negative 4, because negative 4 times negative 4 will give you a positive 16, or it can be positive 4, because positive 4 times positive 4 gives you a 16. And sometimes you'll see that written this way. Right, so the square root of 16 equals, and this means plus or minus 4, positive or negative 4. Okay, you'll see it written like that sometimes. So you're going to see some discussion about that, and then they're also going to talk about the Pythagorean theorem, which is that's a theorem that involves some squares. And so, just as a refresher, if you have a right triangle where one of the angles is a 90-degree angle, and we're going to call this side A, and we're going to call this side B, and we're going to call this side C. The Pythagorean theorem states that a squared, the length of this side, a squared plus b squared, the length of this side, equals the length of this side squared. A squared plus b squared equals c squared. And remember, the longest side, the side opposite the right angle, this is called a hypotenuse, okay? That's the longest side of a right triangle. It's called the hypotenuse. Now then, so, they'll probably give you all sorts of equations to work out. They'll give you, like they do in several other fields that we've talked about this year. they'll give you two of the variables and you have to figure out the third one. Now, this is a particularly important equation in mathematics because it is it's the way that you figure out distance, right? It's the way that you figure out the distance between 2 points. So if you think about it, if you've got, let's say you've got your Cartesian coordinate plane, and you've got these 2 points here and here. Well, the way that and you want to figure out how far it is from that point to that point. Well, what you do is you draw a triangle, and this is going to be your difference in x here, or sometimes you'll see it called delta x. That means change. Delta is used to that's a capital delta, the Greek letter delta. That means change. So delta x, that's your delta x, and it also, so the change in x here, like let's say that this is 2, this is 4. Well, your delta x there is 2 in this case, because it's 4 minus 2, right? So the length of that leg of the triangle would be 2. Now then, this right here is going to be your delta y. That means that's the change in y, because this is your y-axis. This is your x-axis. And so this is your delta x, and this is your delta y. Well, if you apply the Pythagorean theorem, and you use your delta x as your a and your delta y as your b, then what you're going to get is the square root of, you're going to get the distance between those 2 points. So the Pythagorean theorem is very central to the distance formula. And as a matter of fact, something that's very curious is in 3-dimensional space, whenever you're talking about not just 2 dimensions, but and this is not in this lesson, this is extra. Whenever you talk about distances in 3 dimensions, interestingly, it can be derived and shown that, for example, let's say you've got, this is, I'll do my best to draw a 3-dimensional. This is, I think, and I'm going to do my best to remember here. This is going to be, I think it's x, y, and z. And so you've got this spherical space, right? And so if you want to know the distance from z, from the origin, which is where all 3 of these axes intersect, out to a point on a sphere, for example, then what you do is the formula that applies, and it's not intuitive, but it seems intuitive. X squared plus y squared plus z squared equals, we'll call that an r for radius, equals r squared. So it's the sum of the squares of all 3 of your dimensions equals the radius squared. So anyway, this is the distance formula. This is going to be the distance formula in 2 dimensions right here. So this is in 2 dimensions, the 2D distance formula, and this down here is going to be the 3D distance formula. Can you see all that? You probably can't. There we go. Okay, so I got kind of carried away. Okay, so anyway, the Pythagorean theorem is going to be key in the 2D distance formula, and the 3D distance formula, you're at least going to use squares, and you're going to be using second order terms. Okay, and second order, remember, just means that you've got a term raised to the second power. Okay. So there you go. That is equations with x squared and the the Pythagorean theorem. Now then, let's see what 118 is about. And I've already looked, but I have to remind myself. Okay, volume conversions. Okay, we've talked about this already, actually, but I'll give you a quick reminder. So remember, whenever you're doing volume calculations, just like with any other calculations involving units, you can use your units to help you help you make sure that you are doing the calculation properly, right? So, so this is English. That just means the English system, inches and feet and miles and so forth. English volume conversion. Okay, so for example, if you want to find out how many cubic inches, remember that's a cube, that is 1 inch on a side. Or you might see 1 inch as 2 little tick marks. 1 inch on a side. 1 inch, okay? So that's a cubic inch, and if you want to find out how many cubic inches are in a cubic foot, well, what you could do, how you could conceive of that is you could imagine a big box that was divided into smaller boxes. And so this is going to be, I'm not going to be able to do all these, but I think you get the point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there we go. And here's this. And so, you know, if you had, likewise, you had 12 inches on that dimension and 12 inches on this dimension. I'm not doing a great job of drawing that. But basically you can envision a stack of 1 inch cube boxes, right? So just a stack of these 1 inch cube boxes making up this cubic foot, okay? And so there's going to be 12 inches this way, 12 inches this way, and 12 inches this way, okay? So if you wanted to figure out how many cubic inches are in a cubic foot, then if you use your units to get, you know, to help you keep that straight, then you can it will guide you in setting up your math, right? So then this picture's in your book, so maybe I should have just shown you that picture. But so remember, we're looking for cubic inches in a cubic foot. Well, there are 12. Well, that's an M. Don't know why I thought that was 12. There are 12 inches per foot, and you multiply that by 12 inches. And actually what we should do is write inch instead of little hash marks. Inches per foot, and multiply that by 12 inches per foot. And what you end up with is, remember, if we're multiplying our units just like we're multiplying our numbers, then we end up with a cubic foot on the bottom, right? And we end up with cubic inches on top. So it's 12 times 12 times 12. So 12 to the third cubic inches per cubic foot, which is 144 times 12, which is some number. Let's see, that's going to be 1440 plus 288. 827, there you go. 1728 cubic inches per cubic foot. All right, and so you'll be asked to do some other volume conversions between, you know, cubic feet, cubic miles, cubic yards, and all that stuff. Okay, but that's a volume conversion. Remember, volume is in 3 dimensions, and so you're going to have you can envision a box, or it doesn't even have to be shaped like a box. It can be any 3-dimensional space, and it's going to have volume. You know, so you could have a can, a soup can, and it holds a volume of water or a volume of soup. Okay, there you go. So that is lesson 118. Lesson 119 is going to be metric volume conversions. Okay. Now, we talked a little bit about the metric system. Okay, yeah. So they're basically going to be doing the same thing. So if you want to find out how many cubic millimeters, for example, are in a cubic meter, you would do the same thing, right? So you've got, if we're trying to figure out how many cubic millimeters are in a cubic meter, well, you've got 1,000 millimeters per meter times 1,000 millimeters per meter times 1,000 millimeters. Remember, these are just conversion factors, right? 1,000 millimeters per meter. Okay, and so what you have is you've got two quantities on the top and on the bottom of this division, this fraction bar. And so since the quantities are the same, all you really have is 1 here. You've got 1,000 millimeters over 1 meter, and those two quantities are the same. So really all you're doing is converting from one factor into another. If you multiplied this by something in order to find out, how many millimeters are there in 27 meters or whatever, well, whenever you go to multiply that number by your conversion factor, all you're doing is multiplying it by 1, but you're doing it in such a way that you change the units, right? Because 1,000 millimeters is the same as 1 meter, so this conversion factor is really just mathematically 1, but it's a way to convert from units, okay? And so if you're looking for the number of cubic millimeters in a meter, well, it's obviously going to be, this is 10 to the third, right? 10 to the 1, 2, 3, times 10 to the 1, 2, 3, times 10 to the 1, 2, 3. So 10 to the third times 10 to the third times 10 to the third is 10 to the ninth. 10 to the ninth cubic millimeters per cubic meter, okay? And that's not 109, that's 10 to the ninth, 10 raised to the ninth power, because this is 10 to the third times 10 to the third times 10 to the third. So 10 to the third times 10 to the 4, 5, 6 times 10 to the 7, 8, 9, right? 10 to the ninth, okay. Millimeters, not nanometers. Okay, so it's a similar conversion issues or similar conversion topics for the metric system, which again should be easier to work in because it's all based on powers of 10. And that is lesson 119. Then we've got lesson 120. Okay, and lesson 120 is just crazy, man. So lesson 120, I'm going to just put this up here to show you why I don't intend to write any of this stuff down. So you've got all these different solids, right? So you've got different shapes of cones and spheres and pyramids. There's a triangular pyramid, a rectangular pyramid, different shapes of prisms, and different shapes of solids. And they're going to have you calculating the volume and the surface area of all these different things. And the surface area, remember, you need to think about that as the amount of paint that it would take to paint one of these things, or maybe the amount of paper that it would take you to fold a three-dimensional shape that was hollow on the inside. So it's just the surface area is going to be the area of each one of the different surfaces all added together. That's surface area. And then volume is how much would fit inside, how much paint one of those things would hold, a container shaped like that would hold, or how much air, is in there. So the volume, remember, volume is going to be a three-dimensional measure, and surface area is going to be a two-dimensional area. So whenever you're answering questions about surface area, you should be coming up with some sort of a square unit, square inches, square meters, square centimeters, something like that. And whenever you're answering questions about volumes, you should be your answer should include a unit that is a cubic unit, because there are 3 dimensions in a volume and there are only 2 dimensions in a surface area, okay? So volumes are going to involve cc's or cubic inches or cubic feet or things like that. And surface areas are going to involve square units. Okay, so bear that in mind while you're looking at these, and if you have any problems, they should, for each one of these, they should give you, before they ask you the question, they should give you when they ask you the question, they should give you the formula that's needed to calculate the volume, and you just have to plug in the numbers. Okay, so if you have any problems with that, give me a holler. Have a good week. Bye-bye.